Okay, so what we're going to start off with is, let's start off with a review of slope fields, because I feel like we didn't do, I feel like a quick refresher of how slope fields work would be good. Okay, so basically, what a slope field is, it's a way to graph. It's a way to graph differential equations. And you're basically showing the behavior of dy by dx, or y prime, at specific xy points. Okay? So, when you graph these things, okay, when you're making a slope field, you're actually just showing what the slope is doing at that particular point for the main equation. Okay? So you're not drawing a full-out curve, you're just drawing little hash marks to say slope kind of looks like this here. Okay? So in that regard, it's very, I shouldn't say imprecise, but it's not quite the same as it is. You're not drawing a graph, you're just showing, again, behavior. Okay? So let's look at an example. How a typical problem involving a slope field might look. They might start off with an equation and be told to make a slope field for that equation. So we'll start off with something straightforward. We'll do a circle, y squared plus x squared equals 16. And we want to make a slope field for this circle. Okay? So the first thing I'm going to do is I'm going to take the derivative of this. Okay? Now, if I take the derivative of this, I have to do it what? Which way? Implicitly. So what's the derivative of y squared? 2y prime, or dy by dx, doesn't matter which one you use. Okay? Plus, derivative of x is 2x. What's the derivative of 16? 0. Okay?
So wait, y, oh, because you're doing it in respect to y, you do.
Yeah. Okay? So, remember, every time you hit, when you're doing implicit differentiation, unless otherwise told, whenever you do the derivative of y, it's always y. You basically treat it as a chain rule. It's always dy afterwards, okay? So, we solve for y prime here, so I'm going to subtract 2x from both sides, okay? And then divide by 2y on both sides, okay? So I'm going to get then, yeah, I'm going to get that y prime is equal to negative x over y, okay? And so this is going to be what I use to make my slope field right there. Okay? So how this works here, okay? We'll do a small slope field.
Oh, I hate this.
Okay? And we go through and we say, okay, basically we feed in x and y values and see what y prime does at that particular point. Okay? So we could do some easy ones to start with. For example, if x is 0, okay, what's this thing going to be?
Vertical line.
No, x is 0, not y.
Vertical line.
0.
Oh, no, 0.
0, so it's going to be horizontal.
Exactly.
Okay? So I can come through here, and anywhere where x is 0, I can put a horizontal line. So there's one right there, one right there, one right there, one right there. 0, 0, I'm not going to put anything there. Why?
Because there's... It's already line there.
You can't divide by 0.
Well, I can't divide by 0, but I would have 0 over 0. Does that make any sense whatsoever? No. What's a slope of 0 over 0?
Undefined.
It's not undefined, it's indeterminate. It's basically a hole. Okay? So we're going to leave it blank. Now, if I go through and say when y is 0, lots of people are like, oh, it's undefined then. That's true. What does an undefined slope look like?
Vertical line.
It's vertical. Okay? So when slopes are undefined, they're vertical. So here, along the x-axis, I'm going to do the same thing. I'm going to have a bunch of vertical lines, okay, going through there. I'm not, again though, 0, 0, because it's indeterminate, remains blank, okay? Now, I have to go through and I have to do other locations. So a good easy one might be when y is 1, okay? When y is 1 and x is changing, now x is going to be basically kind of inverse of whatever x coordinate you put in. So when x is 1 and y is 1, the slope is negative 1.
I don't understand. I still don't understand why you change the angle, like the angles.
Like, what do you mean? What does the slope of negative 1 look like?
Oh.
It's pointing downwards, right?
Okay.
It's pointing downwards like that. So a slope of positive 1, which happens when x is negative 1 in this case, points upward like that. Slope of positive 1. Okay? When x is 2, the slope of this thing is negative 2, so the slope of negative 2 is going to be more like that. And then kind of come through here. And this is where my ability to draw these things wavers. Okay? What's confusing?
Are you plugging it into y prime? Is that what you're doing?
Yes, I'm solving for y prime by basically just plugging in values of x and y.
Where are you putting the values?
So, for example, this location right here,
Yes.
okay?
You're
This is
putting
where
in
x is equal to 1
and 1.
and y is equal to 1, right?
Yeah.
So y prime here should be equal to negative 1 over 1, which is negative 1. So the hash mark I draw there is what a slope of negative 1 should look like. Okay?
Yeah.
That's what it should be there. So this mark right here, okay, this would be when x is equal to 2, y is equal to 1. So this should be y prime equals negative 2 over 1, or negative 2. And I'm just such a terrible drawer, I'm not going to be able to get a good slope value off of that, okay?
What is it when y equals 2 and x equals 1?
So when y equals 2 and x equals 1, okay, we should have a slope of negative 1/2, okay? So negative 1/2, it should be pointing downwards, but very gently. So it should be very should be something like that right there, okay? Going downwards, but ever so slightly, okay? When x is 2 and y is 2, we have, again, a slope of negative 1. So it should be the same slope as that one right there, okay? And in fact, with this thing here, if I go through, okay, and fill this in,
So it basically is just the opposite on the other side.
yeah, but look at the picture it sort of makes here. They make what? Yeah, they make it look like circles, right? And so you can see there it's kind of like a bullseye. It's a circle. If I connect the dots, I get a circle, okay, for any given thing. And so that's basically how a slope field works.
Do you look
Okay.
at it every time or just most times?
I'm sorry?
Do you look at it every time or just with the majority of the
Oh, no, it looks like this in this case because my original equation was a circle.
Okay.
Okay? If my original equation was a parabola, the slope fields would look like they would make a parabola type shape. It was like x cubed, they make an x cubed type shape, okay, going forward. Okay? There's excellent pictures of slope fields, much better than I could do by hand. You can see on page 408, okay? You can see examples of how these slope fields work. Okay, 408, 409 show excellent examples of this. 408, they have a thing where it's identifying a slope field from the differential equation given. So it's just like a matching exercise. Okay, but then in 409, they give you a slope field and they say, okay, how do I use this slope field to figure out what the original equation looked like? And you just connect the dots and draw, and you get the thermal picture. Okay. But this is how a slope field works. Okay. Any questions so far? All right. Good. So that's really it. That's all there really is to slope fields. Okay. So like on Friday's test, for example, you would just get, you would be say like make a slope field for this particular equation, and you would basically do what I did. Take the derivative, then draw the slope field. That sort of thing. Okay? All right.
Wait, so the slope of that other green one is negative, okay.
Yep. And again, it's just I'm not, no, obviously this is not I'm not a particularly good drawer, so this isn't perfect.
So
But
they
it's
aren't,
just
like,
showing
at
you
the
the
right-
general idea, okay? So like, on the test on Friday, if you were to like, if the slope came out to be like -3, okay? As long as it's showing that you're going downwards, kind of steeply downwards, I'm going to accept that
If
as
it's
good.
like kind of big, you can you write it as fine.
Huh?
If they're saying it's like kind of you write it, but it's kind of hard to distinguish, and you just like write this one next to it.
Yeah, that'd be fine as well. Okay, that'd be good, in fact. All right, good practice, okay? Any questions, though? All right, cool. In that case, what we're going to do here, for the rest of the class is we're going to talk about a particular use of differential equations, okay? And this is what's known, basically, we're going to talk about how the growth and decay model.
This one's us.
Yes and no, but you should still know,
Yeah.
okay? Because this is like one of the, this is a particular use of differential equations, okay? So growth and decay models, okay? Basically, if you remember from last year, from pre-cal, we had, we had lots of equations involving growth and decay. We had a model. So we had things like a bank account with $500 in it, has
Yeah.
3% interest, how much does it have after 10 years, yada, yada, yada.
Wouldn't you use logarithms for that?
Okay, you do, you can, okay? And we will be actually using logarithms here, okay? It turns out though, with differential equations, we can model growth and decay quite nicely, okay? And we're going to take a look at how that works here. It all starts off with a specific differential equation, okay? That is dy by dt equals ky, okay? And here, the parts here is, this is the change in y with respect to time. Okay? K here, okay, is what I'm going to call the growth constant. And of course, y is your amount. Okay? But K is going to be what's called a growth constant. It's going to be, the book calls it a proportionality constant. I think that's is what it is because this is a proportion. But I think it's better to think of it as a growth constant because it's going to determine, you're going to see here very shortly, it's going to determine whether your system grows or decays. Okay? All right, so this is what we get right here. Now we're going to integrate this thing, okay, with respect to time. Okay? So, if I'm doing that, I got to get y's on one side and everything else on the other side. So we're going to separate variables here. So I'm going to divide everything by y. Okay. Get that right there. If it helps, we can move the dt over to the side with the k. Okay, so I'm going to go ahead and do that. Okay. Now I'm going to integrate this. Okay. Now, what would the integral of dy over y be?
Why?
Not the dy divided by y?
Oh, it'd be log.
Yeah, natural log of y is what it comes out to be. Okay? So, this here then becomes the natural log of y equals, and k dt, k remember is a constant, so it's the growth constant. So, what's the integral of a constant? Not 0, that's the derivative of a constant.
It's a constant.
It's constant x. Okay? It's constant x. So in this case, it's constant t because we're doing it with respect to t.
Wait, so how do you know they use an interval there?
Because we're trying to get rid of the differential equation. All I'm doing is showing you how we get the growth.
What does
model.
the KY stand for in the first place?
K is the growth constant, so it's telling you whether the system, it's a constant that the system is going to grow by, basically. And y is just whatever amount you have. Okay? I'll scroll up here in a second. We'll
Okay.
give you this.
So
Okay?
then, is it, did you just like move the Do you multiply the dt out just to isolate the y?
Yeah, basically, that's what we did right here, okay? And you know, sometimes too, you'll see, instead of dy by dt, you just see it as y prime. Just know that when you integrate, it basically works this way, okay? All right, we don't want this to be natural log of y, we want it to just be y, so how do I get rid of natural logs?
Take a log of it, log base e.
Make it the exponent of e, okay? So, if I do that, oh, what did I forget? Oh, I'm being really dumb here.
Plus C.
A plus c, good. Okay, we have a constant c added on. So we go ahead now do the e trick. So it's e to the natural log of y equals e to the kt plus c. This right here just becomes y. This over here we can rewrite as e to the c, e to the kt. Okay. I did that because, one, I'm adding that c on there, and when you add exponents, it's like you multiply their bases, right? So if I have like 10 to the third times 10 to the fourth, I get 10 to the seventh because 3 plus 4 is 7. Well, I'm doing that up there. I'm doing it this way too because remember, this constant c here is just a random constant c, okay? Who knows what the actual number is? It's just a constant. So it's e to the c then.
A constant.
Also a constant, right? So I can replace it with just constant c. And so I get y is equal to a constant times e to the kt, okay? And this here is the equation for growth. Okay? And its particular parts here is y is our final amount. C here is our initial amount. The K is the growth constant. And T is time.
So the initial amount, would that be the same as y, even though dy?
No. That y would actually be the final amount, okay?
Then KT plus C.
And so that's something to keep track of, okay? I'm sorry?
That log natural y.
Of kt plus c.
And how did you go from 1 over y times dy dt to dy over y?
Oh, all I did was move the dt
Oh, you just
over
multiplied
and
the
just
dt.
multiply, yeah.
Okay,
Okay.
got it.
They cleaned it up, okay? Which you can always do in these types of equations.
Do we need to know how to derive it, or can we just know the formula?
Oh, know this formula, you can just know this formula at this point out. Just understand the relationship between, and I'm going to go ahead and create a new slide here. Just understand that y prime equals ky, okay, goes along with y equals c e to the kt, that those things are together, okay? And you'll see in examples, we may not get to one today, but you can use the y prime kt. You know, if you know what that is, you can use that to make a to create your model here, things like that, depending on what information is given to you. Okay. You'll also notice here, because we're going to do an example here in a second after I write up the full theorem here. Okay. The example we're going to use, you're going to notice we never actually touch y prime equals kt, and a lot of times we will not actually use that. Okay. It's something you need to know, but at the same time too, it's something that never actually comes up in our equations, okay? It's sort of just like telling you like how the change in the system is, basically. Any questions there? We'll take a look at that in a second, okay?
Can we do that for like 1 more second?
Yep. We're going to do a real world example. An actual real world example.
Is this it? And then we're talking about the test? I mean...
Well, we're going to talk about the test all day tomorrow.
I mean, is this the last thing?
Oh yeah, this is the last thing that we're ever going to cover with. Yeah, this wraps up differential equations. Okay. That's this particular use, and this is the only use of them. You got slope fields. You got actually doing these differential equations, and you get this. These are the only things that ever appear on the A/B test. Okay, if we were doing BC, we'd have a lot more to do with these. But also, if we were doing BC, we would not have been doing all the stuff we did with derivatives and intervals and their roles, because you should know those by now. Yeah?
How did it come out from e to the c to just c?
Oh, e to the c is a constant. Remember, e is 2.71 and change, okay? And c is a constant, so I'm raising 2.71 by a constant, so it'd be like raising 2.71 by like 5. It just comes out to be a constant number.
Okay.
So I could just replace EC with just any random constant.
So e to the ln, does that just end up being like 1 or something?
Yeah,
1.
e to the ln cancels each other out, okay? So whatever the argument behind the ln is, that's what it becomes, okay? Because you're basically saying, I'm going to raise e by whatever exponent I need to raise e by to get this, okay, is what that actually means. All right, so the actual full theorem here, sorry, gotta move on.
Good, no.
Okay.
Sorry.
Is that basically the growth of the decay model. It's that if y is a differentiable, and you don't have to write this down, it's in the book, function of time, okay, such that y is greater than 0 and y prime is equal to kt, or ky, excuse me, for some constant k, then y is equal to c e to the kt, where c is the initial amount, or initial value, and k is the growth constant. Okay, if k is greater than 0, we have a growth equation. K is less than 0, we've got decay. Okay, and so that's the full model for growth and decay. Okay, all written up nicely together. Okay. All right. So again, this is in the book, page 416. All right, the page number up there. So if you want to add it to your notes,
Yeah, like a
which is
definition
good to
of it.
do. Yeah, this is a definition for you. Okay. But because I want to move on to the actual model.
Sounds good.
Okay, so let's look at an actual example.
Is it on 416?
416, yep.
How much is it?
Okay. Real world example here, okay? At Chernobyl, 10 grams of plutonium-239 was released. Okay. Plutonium-239 has a half-life of 24,100 years. Okay. How long, or yeah, basically, how long will it take for there to be 1 gram? Okay, so basically, we're trying to figure out how long it would take for there to only be 1 gram of this plutonium left, okay, after the 10 grams were released. By the way, a whole lot more than 10 grams were released at the actual Chernobyl experiment. And I'm not sure if it was plutonium they were
It's
using.
uranium-235.
Was it uranium-235? So, which is equally as awful. But you get the idea, okay? So, how this goes through? Well, the key bits of information is our initial amount is 10 grams, okay? So at time equals 0, we would get 10 grams, so C would be 10, okay? Next, we're told we're trying to figure out the time it would take to get 1 gram. Okay. The thing we're missing here is a what?
Constant.
The growth constant, right? Or in this case, the decay constant, actually. So we got to figure out what that is. Now, I'm going to figure that out by using the fact that the half-life is 24,100 years. What does half-life mean?
In 24,100 years, there'll be 5.
There'll be 5 grams. So I'm going to write that up. I'm going to say, okay, basically, we'll say finding K. Okay, 5 would be equal to 10 times e to the k times 24,100 years. Okay, right? Just filling everything. So we're going to solve this for k. Should be fairly straightforward. We divide side by 10, so we get 1/2 is equal to e to the k times 24,100. How do I get rid of an e?
Lid.
Natural log. So I take the natural log of both sides. Take the natural log of 1/2 is equal to k times 24,100. So k then would be equal to natural log of 1/2 divided by 24,100, which is equal to minus 0.00000. Hang on, I gotta get the exact number. 28761. 28761. Okay? That's a really small number, right? Okay. So what does that tell you about the K here? Is it going to take a long time?
Yeah.
It will take a really long time. Okay?
Wait, is that negative?
Yes, negative 0.0000.
So if it's
28761.
how can it be negative? It's time.
No, it's not time we're finding. It's the growth constant.
Oh.
We haven't found time yet. We're about to
So-
figure out the time.
So it subtracts by that many.
Right. So basically, it means that I decay by this growth constant every time iteration, basically. Okay. So let's find the actual length of time it takes. Okay. So to find now the time with 1 gram, we set up the equation the same way. 1 is going to be equal to 10 times e to the negative 0.0000028,761 times time. Okay. So we're going to solve for t. So we're going to do the same thing we did before, except instead of solving for k, we're solving for t. Move the 10 over, like 1/10 is equal to e to the negative 0.00028,761t. Take the natural log of both sides. Oops. Okay. We get then that time.
Wait, is there a T on the end of that puppy?
Yes,
Okay.
that's what those. Yeah. So our time is equal to the natural log of 1/10 over this long number. Small but very small number.
Is there any way you can like abbreviate that?
I'm sorry?
Like when you're doing problem, you have a number that big.
2.8. You could write it as.
You could write it as
times 10 to the
Can you
negative.
like,
Fifth. 10 to the
like,
negative 5, right?
you like let this number equal X or something?
2.87616 times 10 to the negative fifth is what I would write it. Or do you mean like truncate it? You could, if you really wanted to, yeah, I guess if you were like writing this out, you could say let A be equal to this number and then do it in terms of A, that'd be fine.
Okay.
Okay, because you've declared A is this constant. Okay, but when you do all this out, you get then that T is approximately equal to 80,000. What is it? 59 years. So that gives you some sort of sense of the scale of that disaster. Okay.
So, what t equals the natural log of 10 over, or 1/10 over that, that comes out to be 80,000. You just know that that's automatically used.
Yes, because we're talking about this particular problem.
Oh.
We know that because right up here
Right.
we declared the unit of time we're using these units. So If I replace that with seconds, it'd be 80,000 seconds. Okay.
What actually happened in Chernobyl?
So there's a meltdown of the Chernobyl reactor. Okay. Basically, what happens there is the fissile material they're using to make the power. You have to constantly regulate its temperature. If it gets too hot, which it will naturally do because it's basically the atoms are splitting, it'll get so hot it can melt through the container that's holding it. And that's what happened at Chernobyl. Basically, due to poor safety practices, and kind of when they built the plant, they kind of rushed it to completion. It basically melted through its containment vessel, causing a giant fire. When a full meltdown, what happens is the stuff will get so high, it will melt straight down, hit the water table basically, and explode into a giant plume of steam and radioactive material, which is what happened in Chernobyl. So they basically, what they've done there is they built a containment dome around the original site. And to give you an idea of how volatile and gassy this stuff is, they're now building a second dome over the first dome because
So is it
the stuff has melted through the first
Is
dome.
it dome made out of lead?
Concrete and steel and other stuff. The lead's too soft, lead melts. So
Some lead was like.
it blocks radiation, yes, but it blocks it because it's fantastic good at absorbing radiation. However, it's still a metal with standard metallic properties, and the issue here is heat. Okay, this fizzing material is incredibly hot.
It's still in there right
Oh yeah, it's still going. It'll be going for the next,
80,000.
actually longer than that. I think they said like, yeah, it's going to be like a really long time.
How like big is it inside the dome? How much space is inside the dome?
I don't know that.
So I think it's
Have you seen the Vice documentary where they try to hunt radioactive creatures?
Or in the town around Chernobyl? Yeah.
Try to
I
hunt
think I've
it.
seen that.
They get
I've
in
seen, you can go there, okay? If you're feeling
How about
particularly
the guy?
stupid.
The guy in River Monster tried to catch a Chernobyl catfish.
Yes, I remember that.
Didn't
Um,
really catch anything else.
It's kind of an interesting case study because there's a large exclusive zone around the plant that basically, if you lived there long term, you would die.
Mutation.
Not mutation, you would just die from cancers.
We're like a lot of kids like that. You like born with like big toes and stuff like that. Like weird.
No, that's not how it works generally. What happened is with Chernobyl disaster, a lot of the civilian population in the years afterwards contracted really nasty forms of like leukemia and lymphoma and stuff, and basically died from that. Which is typically how radiation kills you. It doesn't mutate you like in the Fallout games.
No, like the kids.
No, even with the kids, it's not gonna.
Really?
It doesn't mutate. No, it's not a mutagen. So basically, radioactivity doesn't. Mutation means the DNA got changed. Okay, that's not what's happening here. Radiation specifically breaks down the DNA. DNA is not a particularly strong molecule, so basically it can be broken apart at the drop of a hat. Normally, you're nice and that happens in you many times per day. It's just that you happen to have a lot of the same DNA in you, and so your system's pretty good about regenerating it and fixing it. Okay, so if one of my cells has its DNA get blasted and Kingdom Come, the rest of my body still has its DNA fine, and we'll go and fix it. Basically, what happens with radiation is you just get so much. You get hit with so much. So much of your DNA is just destroyed so rapidly that your body can't handle it. It also, too, radioactivity also causes a lot of heat. So, and it causes heat in ways that you may not necessarily notice or feel. So, what happens a lot of times is you end up getting cooked from the inside out, and not really realize it until you're kind of dead. Or it's too late.
I wouldn't be there for it.
Yeah.
For the Y amount,
Uh-huh.
For the first one, why did we use 5?
Oh, we used 5 here because we need to figure out what K was.
What's the half?
And we knew that the half-life of the plutonium-239 was 24,000 years. And so 10 was the amount we started with.
That's times.
After that amount of time, there'd be half of it left, which would be 5.
Okay.
Okay?
And then we used the 1 because we wanted to find the time with 1
Right.
gram.
We were told 1 gram. We had to find our constant first, then we had to find the amount of time there would be after this amount of time. If you look this up in the book, by the way, you'll notice this is a common theme throughout these problems. They all work this way, okay, for the most part.
We have to find K first.
You have to find K, then figure out time, or vice versa, or something like that, okay? Almost, very few of the problems actually start off with y prime equals ky, and going from there to figuring out the answer, okay? Generally, when that happens, you'll be told what the change in y is. So you say like y prime is equal to like 15, okay? And then y, at the end of our system, is equal to like 10. So it'd be, you'd solve for k that way, and then use that to figure out time, okay? If you know your initial amount, okay?
Have you drank
Very
that whole
common.
thing?
When did it happen?
I'm sorry?
Have you drank that whole thing?
No. I started this like 2 days ago.
Okay.
I just grabbed it this morning when I was in the house. So this was maybe about a normal amount's worth of ginger ale in here. It's quite-
It happened in the 80s.
Yeah, it's like 86, right?
Yeah.
Can you not just water it down, or would that just destroy everything?
What, watering down the stuff? That's what they did at first to try to contain it. The thing is, it's going to create a ton of radioactive steam. And
Probably
so,
worse for the environment.
well, like all the people who like worked to clean it up are dead. They did not make it because
Being in hazmat suits.
even in hazmat suits. In fact, actually, I was watching a documentary about, it was on PBS, about kind of the history of uranium in general. And one of the the host of the documentary, went with a lady to the city, and they were going around and just seeing like, because one, it's kind of like the city where Chernobyl reactor is.
Wasn't it really nice initially?
It was, and it was like a.
I know I live there now.
It was a great like